I'm going to use the Laplace transform method to find the solution for the second order constant coefficient inhomogeneous differential equation shown here. Little x is to be regarded as a function of t, and the dots are differentiations with respect to t. The equation is inhomogeneous because there's a non-zero function of t on the right-hand side. It also has two conveniently expressed boundary conditions at the value t equals 0. In this case, both given as 3/2. Let's start by setting up the usual notation for the Laplace transform of little x. Remember, we normally call it capital X. With that notation established, we can then write down the formula for the transform of the first derivative and the second derivative. To remember how those automatically incorporate the boundary conditions in a very convenient way. So with the blue, red and green expressions shown here, we can now take the Laplace transform of the entire differential equation. The process of taking the transform is linear, so the left-hand side will separate into three separate Laplace transforms, one for each of the x and its derivatives. On the right-hand side, we've got a function whose transform we'll have to either remember or look up. Okay, the next thing is to replace the curly L's in this black equation with the capital X's. There's only one of the transform of the second derivative, so we'll just want to copy out the green right-hand side with a coefficient of 1. On the other hand, there are two of the first derivative transforms, in fact -2, so that means we'll need to put a -2 in front of the expression there, the red expression. We'll have to be careful with that -2 when we expand the brackets. Finally, there's just two of the Laplace transform of x, and we still have to deal with the right-hand side. Now, how do we go about that? Well, perhaps you remember the transform for cos t. It's just s over s squared plus 1, isn't it? Having an e to the t in front tells us we must use the shift theorem. The coefficient of t in that exponential is 1. It's e to the 1t. So we have to shift s to s minus 1 everywhere in the transform of cos. Making that shift will give us s minus 1 over s minus 1 all squared plus 1. Here I have also incorporated the boundary conditions, x of 0 and x dot of 0, both to be 3/2. So there is the form we've reached so far. The next step is to isolate the capital X on one side of the equation and everything else on the other side. Look at the capital X terms on the left. There is s squared capital X, that's here. There's minus 2sx, that's here. And there's plus 2, that's here. On the right-hand side, I've copied out the term that's already there, but we've got to take some other stuff over. There's the 3/2 s term. On the left it's minus, so on the right-hand side it will be plus. Let's start with that one. What else is there? There's -3/2 and 2 times 3/2. That's 3 minus 3/2 is just plus 3/2. But it comes to the other side, so it becomes minus 3/2. We could put a bracket around the s and write -1 here instead, couldn't we? Okay, next step is to isolate x completely by dividing by the quadratic coefficient. Before I do that, though, I want to notice something about that coefficient. Look at what happens if we complete the square. The coefficient of x is s minus 1 squared plus 1. It's actually the same as the denominator on the other side. Having noticed that, let's write it that way. So here's our capital X of s. In the first term, the completed square quadratic underneath is now squared because it's been divided again by the same quantity. I've written it as a completed square in the second term as well. It's worth asking ourselves what implications this phenomenon has. The fact that the coefficient on the left is the same as the denominator on the right. It's actually telling us something. It's telling us that the function on the right-hand side of the original differential equation must appear in the complementary function when we solve the homogeneous equation. If that's not clear to you, have a careful think about it. But then that tells us something else, and it in fact gives us a clue as to what we should expect when we take the inverse transform. If the right-hand side function is in the complementary function, then if we were solving this another way, say by guessing solutions for the particular solution, we would have to take the right-hand function and multiply it by t, or even worse, possibly by t squared, before we found a particular solution. Let's now remind ourselves, with that in mind, what it means for a Laplace transform when you multiply a function by t. Do you remember this result? If the transform of little f is capital F, then multiplying by t in the transform has the effect of differentiating f with respect to s and including a minus sign. Looking at the right-hand side of our x of s equation, that's therefore suggesting to us that we might hope to find some kind of derivative structure on the right-hand side. With that in mind, I'm now going to rewrite the right-hand side, and I hope you can convince yourself that what I say is true. The second term, the one with 3/2 in, is already exactly how I want it to look, so I'm not going to change that, and I'm going to write it first to get it out of the way. The second term, though, well, actually, it's precisely a d by ds of something. In fact, it's minus d by ds of the function 1 over s minus 1 squared plus 1. If you can't see that immediately, do a bit of jotting on some paper using the quotient rule. You'll see that what I claim is true. Identifying that feature will now make taking the inverse transforms very easy. Let's deal with the first term, the blue one. That's the easier of the two. Can you see that wherever s appears, it appears in the combination s minus 1? That's telling us that a shift theorem has been applied here. We need to revert or invert the effect of the shift theorem. So let's look at the inverse transform of s over s squared plus 1. Well, that one's easy. It's just cos t. But now, the effect of having s minus 1 instead of s is simply to take the cos t and multiply by e to the t. That means that we can now fill in the first step of our little x of t. It's 3/2 e to the t cos t. Now, what about that other term? It's minus d by ds of something, isn't it? That means it must be plus t times something when we take the inverse transform. But t times what? Well, it's not a cos, because that would require s's on top, and we've only got 1 over s minus 1 squared plus 1. But of course the trig function that has a constant on top is the sine. Let's remind ourselves about that. Here's the sine alone. It's the inverse transform of 1 over s squared plus 1. But in our expression, we've got s minus 1's again. That's just another effect of the shift theorem. So the inverse for 1 over s minus 1 squared plus 1 must be e to the t sine t. But now, the transform we've just taken appears here, but there's minus d by ds in front. That means we have to use the answer here and simply multiply it by the t. So there, finally, is our x of t. Let's write that out below so we can check a couple of things on it. X of t is 3/2 e to the t cos t plus t e to the t sin t. Let's factorise that with e to the t as a factor. Now, I think that's probably the neatest form of the solution. I'm not going to check this solution by substituting it back into the ODE. I'd like you to try that though, but I will quickly check that the boundary conditions work. Let's look at x of 0. So this is a check. X of 0 is e to the 0, well that's 1. Cos of 0 is 1, so that's 3/2, and sine of 0 times 0 is also 0, so that makes 3/2. So that checks out. It is the correct value for the boundary condition. To check the other one, we'd have to look at the first derivative of x. I'll leave you to check that the first derivative has the following form. It's actually minus a half sine t plus t cos t plus 3/2 cos t plus t sin t. I've had to use the product rule there. When we put t equals 0, we get e to the 0, that's 1 again. Then we get minus a half times sine, that's 0. T times cos, that's 0. 3/2 cos, but cos of 0 is 1, so that's 3/2. And then the last t sin t is also 0. So that one is 3/2 as well, and that checks out. I'll leave you to check the actual differential equation works.